Hi there, everybody, and welcome. This is Professor Thayer, and today we are going to continue our discussions on quantum mechanics and physical chemistry for the life sciences with our discussion of particle in the box. So last time we talked about the Schrödinger equation, which set us up for this discussion, and today we will proceed with that. So as usual, let me just turn off my video and share my screen and get to the work page. So let's do that, put this down. Now I put those out of the way, and now I should share screen. Share screen. There we go. Ta-da. Okay, good. That's now screen sharing, and now I should put this up. I'm a little paranoid about this entire screen. Okay. And this would be full screen. All right, and let me get my pen out here for you. Oops. So then last time we discussed some important things. We had some key findings. We saw that the Schrödinger equation is related to the classical wave equation. And in fact, we talked about how it could be derived from that. We put into the operator format because that's how we're going to need to solve this. And we saw that the Schrödinger equation is both an operator problem and an eigenvalue problem. And because of that, we had taken a few moments to understand how we could solve the operator problems and the eigenvalue problems, just in case somebody's not familiar with that. So for today, we will have a few more words on operators. And we will solve the particle in the box, which is abbreviated by PID. All right, so for the one-dimensional kinetic energy operator, negative h bar squared over 2m. This should start to look fairly familiar. E squared over the x squared equals the momentum over 2m. This is the kinetic energy relationship to momentum, right? This, by the way, is momentum. case you were wondering. Okay. Next, we're going to do a multiplication. 2m. So when we multiply out by 2m, it goes away on both sides of the equation. Convenient. Okay. 2m. And now we're going to solve e squared equals r squared times. So in other words, this is the momentum operator. Squared operator equals negative h squared. So now after our discussion from last time, you should not be too upset that there's not actually a function here and being an operator. We recognize the fact that there's actually a box here where we're going to fill something in. So this is voila, momentum squared operator. So this means that, let's just recall here, recall that some operator squared is equal to a hat times a hat operating on some function y, right? So it's like this. So what it really means is first the operator would operate on the inside and then this would resolve to something and then it would operate on something else. So we need to talk about how do we deal with multiple operators. And the good news is that it's really not too bad. So if we have example, a hat, b hat, f of x, two operators, just like we had up here. So the momentum operator is really two operators because it's really going to be the first one times the second one, right? So it's like having AB, but A and B just happen to be the same operator for the momentum squared one, which is the momentum operator, which is this thing. All right, so how do we solve this thing? Well, you apply each operator. In turn, from inside to outside. And this really shouldn't be a surprise. This is the same thing you would do in algebra. So if you had an inner parentheses in an algebraic expression, you'd simply just solve the inside parentheses first, and then you'd move to the outer parentheses. Same sort of a thing. So, given is that, here, I'm going to do it. I'm a little inconsistent about which side I put the notes on. So let me do it the same way as I have done it before. All right. So A hat, B hat, f of x is what's given. Okay, and now the question is to go on how do you solve this thing? So now we're gonna indicate the order. So the way you're gonna solve this thing is you're gonna do A hat will operate on the answer of B hat f of x. Okay, show the order. And then, so you would apply B hat operating on f of x. So that will give some answer. So that will give some A hat. And then when B hat operates on f of x, that will give some new function g of x. So now we have A hat g of x. So now we're going to, well, what happened? So we applied B hat to get g of x, some new function, and now we have A hat g of x. And now we would apply A hat, which is going to give some h of x. Right, so that operates on it, and we should all have equal signs. H of x. Okay. What if there's a squared operator? Uh-oh. Like B hat squared. How do we do it? So, oops, A hat squared. Right. So when we have A hat squared f of x. All right. So basically, you just sequentially apply same operator. So really what it means is you have, okay, A hat squared given. Okay, now, oh, A hat squared f of x. All right, now you're going to apply it out, So that really means A hat times A hat of f of x. And by now we should realize this really doesn't mean A hat times A hat. This is A hat operator operating on these things. So what we're going to do now is we're going to show the order. So just like doing it sequentially, you're just going to do it in order. So you're just going to do it like this. So first you take the first operator and you operate on f of x, and then you're going to apply the second one. All right. So A hat f of x is going to create some g of x. So apply inner A hat to get some g of x. So we have A hat, and now when the inner A hat operates on f of x, it's going to give g of x, right? Like that. Oh, did I do the parentheses above? No, all right, so I'll just try to be more consistent. So I didn't put the parentheses the last time, so I won't put them either. All right, that's fine. So now we have A hat g of x. So now what do you suppose we do next? Now we apply the outer A hat. So now we get h of x. So yeah, fgh. Yep. We get some h of x. And that's how you would do it. And we should put equal signs there. That's how that much. Just as a note, a hat squared of x is not going to be equal to a hat squared for an arbitrary. So what you can't do is you can't just assume you're gonna take like a hat f of x and then square that thing. That may or may not hold true. All right, so suppose, getting back to that momentum operator, we want to get just the p hat. So you can achieve this by taking the square root of the p hat squared. That will work though. So let's see. So let's just work in only one dimension. So we'll do px hat. So this just means we work in the x direction, equals negative h bar squared b squared over the x squared. This is of. Let me recognize this as an operator and realize there's an open box here to substitute in some function, right? Okay. So now what we're going to do is we're going to take the square root. Square root. Oh, we have a negative sign here. What happens when you take the square root of a negative? All right. Now we're going to need to do some factoring. And also recall that I squared equals -1. So if we have multiple factors, like the same thing inside here, then we would be able to pull it outside the operator. So this actually factors. So h squared. And okay, h bar squared is good because we can use h times h. Now d squared dx squared would be like, it's not exactly multiplying, it's applying the operator 2 times. So that can do, and the negative is really going to be, all right, negative is I squared. So to take the square root of this, we're going to need I. So with these things in mind, what we can do is we can do negative I h bar ddx. You agree? Times negative I h bar ddx. All right. So now okay, and why do we introduce the 2 negative signs? Yeah, introduce 2 negative signs because when we square it out, we'll get -1, and we need to have the original sign come back. So that's why we need to put, yeah. So we need this to multiply to plus. So the original negative sign will come from the I times I equals -1. So when we apply this square root of px squared, next what we're going to get is equals I h bar d dx. So this is how you can solve, for example, for the momentum operator using operator mathematics. There are other operators as well that are also defined as squares, so it's useful to see how this might work. All right, so that's how you would do that one. All right, now we're finally ready for particle in a box. 1D box, otherwise known as PIV. Now, the thing about the particle in a box is that in one dimension, it's actually particle on a line. Particle on a line, because it's only 1D. So there's only certain places where it can go. Let's draw a picture to understand what the setup is really like here. So we're going to have some axis down here, right? X-axis. And we're going to have some boundary. Like so. And I'm going to have some other boundary over here. Okay, this is infinity. Draw it like this. And here's our particle, which can move in either direction. All right, and then we have some position A here and some position B here. All right, so I just drew a little picture of our particle in a box scenario. So what we've got here is we've got the x-axis here, and here's our particle sitting on the x-axis. And this particle is able to move between the bounds. Now, these are the boundaries over here, which are infinitely high. And the boundaries cannot be the particle can't go in the boundaries, right? So the particle is going to be somewhere inside the boundaries. But the question is, where's the particle inside the boundaries? Now, because I've drawn it like this, you might think that the particle actually could move around all up in here, but actually it cannot. The particle can only move back and forth on the line. This is for the 1D. If you want to talk about the region, then we need to have the 2D particle in a box. This is the 1D particle in a box. So this is an infinitely high wall. There are two of them. So our situation is like this. There's a free particle of mass m. What we mean by free particle is the particle is able to move. It's not like attached to anything, so it can move across on this line. Particle constrained to x-axis between x equals 0 and x equals a. This is the upper boundary, 0 to a on the x-axis. And yeah, these are particles. Right there. And it's moving back and forth. The free particle implies that there is no external potential. Now, remember we talked about some of the assumptions that we're making as we go along. This is certainly going to simplify our situation. So in other words, i.e. v of x equals 0. This means one of the terms of our operator we can set to 0. So if there's no potential energy, that means it's going to simplify to the kinetic operator. So let's see how that would play out. The PID Schrodinger equation has no potential energy. Means the external field is 0. In other words, we can mathematize this up like so. So we're going to have d psi squared x dx squared plus 2m, that's going to be the mass of the particle, e over h bar squared. So this plus should really be between them. More clear. X 0 or 0 is less than equal to x is less than equal to a. Right, so this says x is on the line here, and let's just, I've been kind of drawing the size more fancy. My size and x's look kind of the same, which is a little unfortunate. All right, that's an x, 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 and x. All right, we got 3 x's. This is 4. 0 is between x. X is between 0 and a, which matches what our picture said. We'll be looking for the solution to this equation, which will be a psi of x. Wave equation. Right. What is the interpretation of the wave function? X. What does it all mean? Why do we need to get this? The amplitude of the wave is classical interpretation given by right. So, but what is amplitude? In QM, then psi of x means amplitude of a particle. Does that raise your eyebrows too? What the heck does an amplitude of a particle mean? Well, that's a little strange. Might have a question about that. What does it mean to have the amplitude of a particle? All right, well, let's go through and let's try to understand what this might mean. It has a relation to the intensity of the classical proportional, to the classical interpretation proportional to the amplitude squared. It's interesting that we're back at intensity because one of the problems we had started with at the dawn of quantum mechanics actually had to do with the intensity. Different problem, but this will be proportional to the amplitude. So you see why we needed to take a moment to look at operators squared because they keep showing up. So the intensity, this is the proportional to symbol. This is the length. That's the amplitude squared equals f squared. Right, so let's just break this down. This means proportional to. So it's like as one increases, the other increases, but it could be multiplied by a number. So it's not exactly the same change, but it's related to. So this means proportional to. And don't forget these double bars means length or magnitude. Okay, this is what that means. This is from algebra. It's in linear algebra, it's the length of a vector. We will consider the analogous psi star of x psi dx. Okay, all right, so we need to make another note. This is for complex conjugates. So this means that there could sometimes be an imaginary part allowed. So instead of just saying psi squared, we're going to say psi star psi. And the reason is because we're now indicating that a solution could have an imaginary part, and that for some of the more difficult ones will actually be the case, which is why some things show up as real answers and some are imaginary, and how some things seem to pop in and out of existence. We're not going to get into that in particle in a box. It's a little more straightforward in this situation. But what's the intensity of the particle? I would like to know. All right. So the intensity is going to be, it's going to tell us about the density of where the particle could be. So it's something like this. Parabolas, remember those, useful for ax squared plus bx plus c. All right, so this is going to be the intensity. The intensity I. And we're going to have some markup here. And there's going to be some parabola. We'll imagine that's a perfect parabola. It's not totally perfect, but kind of close to it. Well, the intensity is going to be some kind of like an upside down parabola. Now, the thing is the negative part doesn't actually mean anything. Here's the x-axis, and here's the intensity over here. See, what we're actually going to be interested in is the area under the curve. The area under the curve is the probability that the particle is located at position x. I is proportional to psi star psi psi dx. So in other words, what we're going to be thinking about is, remember your Riemann sums from your calculus lessons, where you took the area on the curve using the Riemann sums. It's going to be something like this, where you're adding up the area under the curve. Oops. The thing about this pen is that the squiggles are interpreted as crossing things off sometimes. Sometimes it doesn't really. Let's see. Area under the curve. There we go. So all of this is that area under the curve filled in. We could even use the pen to make this a little more emphatic. How about a nice green color? Let's color under the curve, right? To give that idea. There we go. All right, that's what's happening there. I'm going to take the area under the curve, and that is going to be proportional to the answer that we're looking for. All right, good. We can solve particle in the box using the usual procedure that we've done before. For second order linear homogeneous DFQ. Seen this before, right? All right, so let's do this. E squared psi of x over dx squared 2me over h bar squared psi of x equals 0. This is second order linear homogeneous differential equation. PID equation is a second order linear homogeneous DFQ. All right, so what do we need to do? Well, now we need to match up y double prime plus how many y primes do we have? D, so here's the d squared, that's the y double prime. I don't see any d dx, so it's 0 y prime plus, now here's just a plain y, so we're going to have 2me over h bar squared y equals 0. This is in the more standard form. So now we need to ID P and Q by inspection. Right, so now what this says is that P goes with the y prime, so P equals 0 and Q equals 2me over h bar squared. All right, now step 2. This one is step 1. This is given. Okay, so step 2 is use the auxiliary equation. Right, so m squared plus pm plus q equals 0. This is auxiliary equation given. And now the next thing we do is we sub in m squared plus 0 m, so sub p 0 and q equals 2me over h bar squared plus q equals 0. That's the substitute inversion. Now we have ax squared plus bx plus c equals 0. That's the quadratic. This is quadratic. And how do you solve this thing? So the quadratic equation. M equals negative b plus or minus root b squared minus 4ac all over 2a. Then we're gonna sub in. So what's the b? The b is 0 plus or minus the square root of b squared, 0 squared minus 4 times a. This definition a is always 1 because we clear our second order differential equations to have a be 1. And c is this 2me over h bar squared. And this is all over 2 times a, and a, as we said, is 1, is the sub in. To solve m, okay. By the way, this m here is the mass, which is not the same m as our generic m for this equation, just to be clear about that. All right. So let's see if we can simplify this at all. 0 plus or minus. Okay, well, I guess we don't really need the 0 anymore, so we can get rid of that. 0 squared is just going to be 0, so it's going to be minus. And now 4 times 2 is 8me over h bar squared. And this is all over 2. Oops. 8, that's already solved. It's just 2 times 1. This is a simplify. All right, and so now we can take the square root of this stuff. So this is going to be equivalent to, now we're looking to pull out things that are squares. So the minus sign, the square of that is going to be I squared. So let's write this like this. So I squared is I squared, if I can write it correctly, I squared is equal to -1 times 2 squared times 2 mb over h bar squared. That's all underneath the symbol, just in case. The 2 equals. So now that means we can pull out a 2i root 2me over h bar, just an h bar. And then this is all over 2. So that means we now have that canceling out. So the final answer, this is all simplified. So the final is plus or minus 0 plus or minus root 2me over h bar times I. Now this is useful because now remember the next thing we need to do is we need to have our m equals a plus bi. So we need to take this form and match it up. So a equals 0 and b equals plus or minus 2me over h, right? From this generic form, just matching it up. So get a and b by inspection. Yep, it's complex roots. We get a plus or minus, so we're going to have to deal with complex roots. This is the case 3, complex roots. So what do? We select the correct form. and sub in. So all of this is just getting back to that handout we had about solving linear homogeneous second order differential equations. So the solution is gonna be y of x equals e to the ax times c1 cosine bx plus c2 sine bx. All right, this is from the form. That's the general for case 3. And now we're gonna sub in. All right, so let's not scroll too much so we can still see y of x equals e to the, what's a? It's 0 x times c1 cosine. Now we have a value for b. Root. Oh, this is missing a square root sign. Sorry. Cosine of root 2me over h bar x. That's c2 times sine. Same thing. Root 2me over h bar. Okay, let's just see where I missed that. Okay, yeah, see, I just missed it. It's a copy error. Okay. Okay, that one is sub in. And just to be consistent, this one has open close parentheses here, so we'll do sine like that. And there should be an x here. All right, so I think we got that correct. Open, open. So there's 1, 2, 3 opens and 1, 2, 3 close. All right, good. So that's better. Now anything to the 0 power is 1. So that goes away. Good. So now we can simplify this. And y of x is actually our psi. So that's the generic thing. So we could actually say psi of x, because psi is just the name of our generic solution, just because we feel like that. So we're gonna say psi of x. Now we could have a simplified version of this c1 cosine 2me over h x plus c2 sine root 2me over h bar x. Now we have some constants here, several that are kind of complicated. So what have we got here? We got this thing. Oh, this is missing a bar. There we go. And we have another constant over here. So those are all gonna just be numbers. So what we can do is we can make some substitutions to make our life simpler, because who wants to keep writing all those letters, especially if it's just simplified to a number. So let k be defined as root. Did I forget the root sign again? Yeah, I did. Sorry. Root 2me over h bar, and a will be defined 1 and b will be defined as c2. Why are we doing this? I mean, they're all constants, right? Well, just to be consistent with the physics book, so we get the same thing. So if we sub those in, sub in our substitutions, we get psi of x equals, now c1 is going to be a cosine. Now this whole complicated thing is defined to be just k plus b sine ax. Wow, That sure got a lot cleaner. Now, after we solve these things, what do we do next? Well, same thing we always do, apply the boundary conditions. So the first condition, psi of 0 equals 0. This is the condition 1. And let's see what will happen. So sub psi of 0 equals 0 to the equation. So here we go. Psi of 0 equals a cosine k times 0 plus b sine k of 0 equals 0. There it is. Now, do any of these things go to some predictable values? Well, they sure do, because we are multiplying by 0. So the cosine of 0 goes to 1. And the sine of 0 goes to 0. All right, well, that's going to make our equation a little simpler. So this will result to just a plus this thing, all right, so b times 0 is 0 equals 0. Or in other words, a equals 0. This is the result for the first boundary condition. All right. Now let's apply the second boundary condition. At a, it also equals 0. So that means psi of a equals a cosine ka a plus b sine k times a equals 0. This is just sub in the boundary. Sub in the condition 2. All right. Now, we already know some information, however, and that is that we know that a equals 0. So that means we're going to substitute in a equals 0. Psi of a equals 0 cosine k a plus b sine k times a equals 0. I guess we don't actually really need these parentheses anymore. We could get rid of those. These parentheses aren't totally necessary, so we could even do that. All right, so good news. This term goes away. That'll just be 0. So that means that our psi of a equals 0 plus b sine ka. All right, so now that we only have one term here, and we know that this thing equals 0 using the properties of 0, this is simplified. One or two things has to be true. Either sine of ka has to be equal to 0, or b has to be equal to 0. That's the only way we could have this term be equal to 0. Two choices. B equals 0, which is trivial. Gives that psi of x equals 0 for all x. It's really not interesting. So I guess that means there's like no particle in the box after all, because it's never anywhere. So yeah, that one's not that interesting. The particle's always in the boundary, which is, yeah, doesn't really make sense. Or sine Ka equals 0. Okay. When is sine x equal to 0? When x is 0. So it's going to be quantized. Use our quantization again. Ka equals n pi for n equals 1, 2, 3, and so on. Right? Because remember, the sine function is going to cross the it's going to cross, right? So this means that the height is 0. So in the sine curve, you got something like this. Oh yeah, and the problem with this pen is that it thinks that I'm crossing things out, usually. All right. So where will this happen? This will happen at pi, 2 pi, and so on, right? So this is where n pi crosses. And that's why we have this solution, right? So, and this is where the quantization came from. Isn't that cool? I think that's really cool. Then, so just like we did in the classical system, then subbing in what k is. Remember, we just made the substitution above. We can solve for the energy. So what we're going to do is we're going to isolate E. It's an algebra problem. And recall that we had the substitution for K up above here. Made a K substitution right here. And so we're going to reverse that and bring it back out because we actually need to know what's inside of there because we like to get E. So now, in other words, we have root 2me over h bar times a equals n pi for n equals 1, 2, 3. And we just brought along the substitution for h bar, which we had written up above. So I just substitute that in. All right, well, how do you solve this thing? All right, well, it's an algebra problem. Remember how to deal with things. Variable is under the square root sign, right? We want to solve for this one. How are we going to do that? I'm going to do some algebra. All right, so what we can do is we can move a to the other side. So root 2me over h equals n pi over a. And I'm not going to keep rewriting for n equals 1, 2, 3, right? That applies to everything. We will put a little arrow there at the end to remind ourselves of that. So I just divide by a to get that. And then I'm going to square out. Square both sides. So equal. Okay. Oh, yeah, we could also move the h over. Would you be horribly upset if I did that all in one step? I hope not. It will make my life a little easier. Okay, so I'm also gonna just move the h over here. So it will just go up there. Okay. divide by a, and multiply h. Okay, so now the h is on the other side, and we only have just the square root part left on the left. And the e that I'm looking for is not isolated yet, but I'm getting there. So what I'm going to do is I'm going to take the square of the square root of 2me. That will be inverse operations to undo the squaring, but whatever I do to the left, I have to do to the right. So I'm going to do that. Okay. So this means now I have, because I just brought this out of the square root sign, this means I have plus or minus 2me equals, oh, right. And oh dear, sorry, I forgot to make that an H bar. So I'm just going to go back and correct that. H bar. Okay, so now we have plus or minus 2me equals, now all these things are going to be squared. Oh wait, why do I have a pi in here? And I'm missing, oh no, I do. It's 3 symbols. H bar, pi, and just checking to make sure everything's good. I have the same thing, it's just in a different order, which is equivalent. All right, so I'm just going to write these in the more standard order. H bar squared, n squared, pi squared over a squared. So we're almost there. And also we can reject the extraneous. So that'll be great. We can get rid of that one because we don't need the negative. So, okay, that's great. And so then we can also move the 2m to the other side. So I'm also gonna just divide out by 2m. Okay, this will square out. Okay, and now I'm gonna divide by 2m. So I'm now gonna have e equals h bar squared squared pi squared over 2a squared. This, by the way, is the constant a, not acceleration, just in case you were wondering. All right. So, do you remember that last time when we solved the classical equation, what we did then is we then made the energy levels. Well, we're going to do something similar to that right now. So what we want to do is make sure we have the correct pen. E equals so what I'm going to need to do is h bar squared. So remember, this is Planck's constant, but we got lazy to write it out every time. So we had made a substitution. So I'm going to back substitute. E equals n squared I. Oops. When you look at your writing when you're writing, so you actually make the right shape. N squared I squared h over 2 pi h over 2 pi. Okay, so what I did is broke out the h bar squared, right? So the h bar squared is this thing right here. Oh, no, it's not there. It's this one. So my order is a little bit different, but in a multiplication, that's okay. I just made that substitution there. Okay, so h squared, h bar squared is I multiplied out by h over 2 pi, but because it's squared, I wrote it 2 times. All right, so that's what just happened there. And n squared and pi squared, I just copied down. And now I need to finish over 2ma squared. But the good news is that there's some canceling. Okay, so the pi's, this is the reason why I wrote it out. The pi's now cancel out. So this pi and this pi cancel with the pi squared. So the pi's are gone. No more pi's, guys, sorry. So now we get energy equals squared plane h squared over 2ma squared times a quarter. This 1/4 is because of the division by 2. Do you remember you're multiplying by fractions rules? So if you have it in the denominator of something that's actually all in the numerator, it's really goes down to the denominator. Fraction rules. Applying rules of fractions. Okay, so there's that. Now, energy equals, this is starting to look kind of familiar. N squared h squared over 8 and a squared over n equals 1, 2, 3. And what does this say? G is quantized. All right, so this actually is a very important result. So let's just unpack this a little bit. So Planck and Bohr had independently had introduced the idea of quantization of energy. And that was an empirical idea that they said, I wonder if this would work. Seems to fit the observations. It was totally empirical when they decided to do that. But there was no proof that quantization was actually something that we needed to do. Like they just said, well, empirically it fits, so let's give it a try. But from the particle in the box model, we can see that the quantization actually fell out as part of the answer. And here it is right here. We have just solved the particle in the box and we see that the energy is quantized because we have just solved for energy right here. So when we solved the Schrodinger equation, we got out the answer, right, for our psi function. And then we went back, we had made a few substitutions that sort of hid the energy, made it buried inside the constants, but we were able to back calculate that because the energy is actually in the K. And so we pulled this K back out into its, by breaking it out into its individual terms, and then we were able to solve for the energy for that. And when we actually solve this energy, again, we wind up with this a kind of an equation where quantization is very much a part of that. And so energy came out as a result instead of being something that was postulated. That means that now we know the reason why it's quantized instead of just having it be an idea like, gee, this sounds like a nice idea. So from the particle in the box model, the quantization falls out as the solution with the sine cosine part introduced as the solution to the second order linear homogeneous differential equation because the discriminant of the auxiliary equation is negative, which has the sinusoidal solution. So let's just take a look at that. So remember when we solved our particle in a box, we solved it using our regular steps. And here we're looking for the discriminant, right? So the discriminant's got a negative sign in it. And because of that, when we go to apply the case of the roots, we have the complex roots. So we're going to get the sinusoidal result right here. So remember, in other cases, you may not have a sinusoidal result, but when you have the complex roots, you get the sinusoidal result. And because we have the sine function, that, and then after we apply the boundary conditions, that's where that quantization comes in when we had that answer, right? So here are the boundary conditions. The first thing we did is we solved for when we're at 0 and we saw the a equals 0, and then we took condition 2, and this is where things started to get interesting. The cosine a cosine ka went to 0, but the sine term did not go away. The reason this went away is because of the first boundary condition, which we subbed in right there. And now we take a look at this. We either have b equals 0, the trivial solution, or sine ka equals 0. And here is where we have the introduction of the sine curve right there, which is where the quantization comes from. So then when we back substituted, we still had this part about the quantization in here, because we have the n having been introduced because we had a sinusoidal result for this. So using this Schrodinger's formulation, the quantization of the energy levels is a result rather than an assumption. So let's just try to capture a couple of those thoughts. Okay. And the cool thing about this is the particle in a box is not an overly complicated system. Some of the other things one could solve for are going to be pretty complicated. But this is a pretty simple system. Lessons from the particle in a box. Planck and Bohr introduced quantized energy as an idea based on empirical observation. But from the PIV, particle in a box, quantization comes out of the solution. Because we have the sinusoidal answer. Sine answer from solving the linear homogeneous second order linear homogeneous differential equation with a negative discriminant, which led to case 3 imaginary, which has the sine and cosine solution. Then when adding the boundaries, led to just the sine part, which led to solution which is quantized and is introduced. Right? And that's how that all happened. Stepping back for a minute. We realize we assigned the boundary coordinate. And found that a equals 0, which led to a equals 0. So we can rewrite the equation. In the more specific form. because we know one of the constant values. So we have psi of x equals a cosine kx plus b sine kx. This was the general PIB solution. But what we haven't done is we haven't said about the boundary. So now we can do psi of x equals 0 cosine kx plus b sine kx. All right, but when we sub in 0, of course, this term goes away. Great. So now what happens? So psi of x equals sine kx. Ta-da! Particle in a box equation. Very important equation. All right. Make that nice and neat. Okay, good. Now we can plot the psi of x to see what the waves look like. All right, so this isn't so bad. Psi of x equals b sine x. K is defined as, this is from above, K is defined as n pi over a, for n equals 1, 2, 3, blah, blah, blah. This is from second boundary condition. So in other words, we can set that in, get psi of x equals b sine n pi, n pi over a x for n equals 1, 2, 3. This is just subbing in. Now we can solve it for different n's. So it would be something like this. Here we will have psi of x equals, and I'm going to purposely do it a little bit spaced out, b sine n pi over x e equals n squared h squared over 8ma squared. This is going to be kind of like a little table. All right. So this will be some psi sub n. Now let's do our first harmonic. Psi 1 of x equals. So this means n equals 1. In other words, this here, n equals 1. Okay. Equals b sine 1 pi over a x, and e sub 1 equals n squared, which is 1 squared h squared over 8ma squared equals h squared 8ma squared. Okay, next one. Psi sub 2 of x equals, yeah, I guess we don't need 2 equals. Sine 2 pi over a x e sub 2 equals 2 squared h squared over 8ma squared. Okay, 2 squared is 4, so we're gonna leave this. I'll show you in a minute. You might say, oh, cancel, do your canceling. H. No, you don't want to cancel, and I'll show you in a minute why we don't want to. Okay. What I'm gonna do. All right, I'm gonna leave it. We're running out of time. I'm gonna leave it to you to calculate for side 3 and side 4. Okay, I'm gonna tell you the answer over here. E3 9h bar squared squared over 8ma squared. And this one is 16h squared over 8ma squared. Okay, this is really cool. Now, you can take these and you can plot them. All right, so here we are. This is 0, so this is 1. This is 2. Okay, yeah. Now, this is going to be the number h bar squared, so I need to bring this over to the other side. And we need to have this here. And we're going to need to have, I feel like there might be some straight edges in this. It might help me draw it more cleanly, but we'll just pretend that's perfect, right? Okay. And it should be about the same width in there. Not exactly the same width, but we'll pretend. Okay. 2, 4, 6, 8, 10, 12, 14. I need to go all the way up to 18, 16, 18. All right, so this is maybe a little taller than I need it to be. Okay, and this is gonna be in units of h squared over 8ma squared. Okay, so what we're going to see is we have just solved for our energies over here, and we see that we have these falling at some specific numbers. This one is going to be at 16. So we're going to have one here. Here, and I think I'm going to do, this is mainly for me to help myself remember how to draw this. 16, 9. So we'll have a 9 right here. Right, so we have a 16, a 9. We have a 4. We have a 4, so we have one there. And we also have the ground state. And we also have a 1. Okay, so this is not actually a 1 over here. Erase, erase. Yeah. Okay, good. That's what I wanted. Now, on the 1 line, yes, so we don't really have a 1 line here. I'm going to have to sketch it in. What we're going to do is now we're going to have a standing wave. So, oh, actually, I guess we do have a 1 here. It goes like this, and we have a standing wave. Does this picture look familiar? You've seen this before. You should remember this one before because we had a very similar answer in classical. And this goes here like so. And so now the shape of this is kind of more like a Gaussian. So I'm going to try to sketch this. This is supposed to be sort of like a Gaussian. Okay, it looks a little more pointy than it probably ought to be. But it's a Gauss, it's like a Gaussian kind of shape. This one, all right. Now at 2, which is going to be at the level of 4. Oh. All right, we're gonna have a sine wave. Okay, so unfortunately this is gonna overlap a little bit. Okay. Yeah, that should have been more even. Let me try to do that better. Recognize just that. Let me try to make a better sine wave with the middle right there. Does this look familiar? Okay, and now we have the psi star psi, which is gonna be right here. So this one has a sort of like a double Gaussian kind of a shape. Okay, and this is because these are the psi star psi's. Okay, these are the psi of x, and these are the psi of x squared. It's like the length of that, and that's because it's like psi star psi. Okay, and because we're like sort of squaring these things, that's why these are going all up to the positive on this side. Now it's going up higher at a more rapid rate. So this one is psi 1, this one is psi 2, and now we have a psi 3, which is at the 9 level. So how did I get these numbers? Well, that's because I'm putting them in units of h squared over 8ma, which is from those solutions just right above that we had that I just scrolled past. This is psi 3. And so psi 3 is going to have 3 nodes. Now, do you remember we had something similar to this when we had the other wave equations? So this means we're going to have 3 peaks. So it's going to be like this. This is just for my drawing to help my drawing look a little better. So there's not really that. It's sort of like Gaussians. They're not sine waves exactly. It's kind of, yeah, this is much more pointy than it should be. It's more like that. But I think you get the idea. This is the third one. These are the ends. N is 1, N is 2, N is 3. And then you see how quickly the energy levels go way up. That could be more dramatic. Maybe I should put my scale a little bit. All right, there's 4. And so now we're going to have 2 sine waves. It's going to be like this. Okay, it thinks I'm crossing things out, but you saw what I drew, right? Okay, it goes here. So I think if I draw this separately, maybe it's not going to recognize this crossing out. Good. Okay, and so that means that I'm going to have 1, 2, 3, 4 these funky bumps. Ah, I'm crossing stuff off. All right. So at the 16 mark. All right, 1, 2, 3. How to trick your pen. Okay, so that's all one line, but it's deleting my line because it thinks I'm crossing stuff off if I don't. This is the psi of x. This is our wave equation. And these are the energies. Energy distributions. Runs from 0 to A, and again, this one runs from 0 to A. These are x values, and that's the x value. These are the waves. And these are the probability density. Is the square of the wave. It's not exactly the square because of the whole psi star psi business, but effectively in the particle in a box, it behaves as the square. It's approximately the square, just there could be imaginaries in there. All right, so then what this tells us is this tells us that the probability density under these curves is telling us where the particle's gonna be when n in the quantization So the true answer then is going to be the superposition of all of these things. So we're going to have this one density, and then we're going to have all these other densities. And so where is the particle at? Well, this is telling you the probability of where the particle could go. So again, this came out of solving the particle in a box, and the energies are quantized, which is as we see here with the different energy values. And the quantized energy is what had been hypothesized to be the situation, but it really fell out of the solution of the particle in the box as part of the solution to the math problem rather than being a postulate as it had originally been. So this was a really big advancement for quantum mechanics and really gave some validity to the fact that people were on the right track for how all these things should work. Alrighty, so I'm gonna stop sharing and turn my camera back on. All right, so I hope you enjoyed solving the particle in a box today. It has been an adventure getting here because we did need to learn some math skills before we could do the particle in a box. So thanks for understanding the Schrodinger equation with us the last time, and this time now we were able to actually advance to actually applying the particle in the box, and we do have this really cool result now that about the quantization of the energy, which is of course something that is really important and a fundamental idea that came out of quantum mechanics, because that's all where the quantum part came from in the whole quantum mechanics. All right, thanks so much for joining us today. We will see you the next time.